Hi there, I'm Hao, and this is just another video of me solving random code problem. So let's begin. So today we have to construct um a binary tree to binary tree. So the binary tree is input is represented in an array, and we are asked to convert the array back into the tree node, right? So we are given the preorder and the inorder array. So um preorder mean we process the root first, right? The left and the right. And for the inorder, we processing the left, the root, and the right, right? So if we look at the array right here, we can see that 3 is go first, right? Then we process the left, which is the 9, and then whatever is on the right side here, right? So if there are like more node over here, then we would process this first before we process the right side, right? And again, we process 20, which is the node first, right? The left 15 and the right 7, right? Similarly, for the inorder, we always process the left first, then the root, right? And then we go here, right? Before we process the root, we process the left first, right? And then the root 20, and then the right. Okay, so how could we do this? So a common pattern that we can see is that whenever we are looking at the pre-order array, right, the first element will always be the root, right? Because we process the root first, right? 3 is the root because we process the root first. But if we find the value 3 um, in the inorder array, right, which is here, then what does it mean? It means that the root is here, right, in the inorder array. So everything to the left of 3 is is in the left subtree, right? And everything on the right of 3 will be the right in the right subtree. So using the strategy, we can reduce the available rank, right? As we iterate down the tree. So let's look at an example here. So let's say we have I'm just gonna rewrite this so it's bigger. So we have pre-order, right? Is 3, 9, 20, 15, and 7, right? We're gonna have an index looking at this one. Right? And yes, let me also write down the index to be clear. So 0, 1, 2, 3, and 4, right? Same for the inorder. We have 9, 3, 15, 20, and 7, right? And of course, our index 0, 1, 2, 3, and 4. Okay, so we always look at this. Uh, we will start at the first index, right? Index 0, right? So we will start. We also have the two pointer, the left and the right, right? Because at the beginning, everything is available, right, to be built. So we can start, right? We can start at the first value of the preorder, which is 3. So we say the first value will always be the root, right? So we build 3 here, right? And we start out at 0 and 4 here for the inorder array, right? Okay. So after we create the root, we will increment the index. Oops. Uh, we will increment the index to 1. So now we are looking at 1 here, right? Okay. So after we create the root, we need to keep going down, right? So how do we figure it out? How to go down? So if we find the index of if we find the index of 3 in the inorder array, right? As I mentioned earlier, it is here, right? So we know that everything on the left side will be in the left subtree. and everything on the right side will be in the right subtree of the root 3, number 3, right, with a value of 3. So we can update the range, right? If we go left, the lower bound stay the same, but the root is here, right? The root is at index 1, so the right bound become the index at the root minus 1, right, which is 0 and 0. Right, 0 and 0, which is this number here, right? And similarly, when we go to the right, then the upper bound stay the same, but the lower bound become the index at the root, right? Plus 1. So 1 plus 1 is 2, right? 1 here plus 1 is 2, right? So in this interval, 0 and 0 is on the left subtree. In the interval from 2 to 4, from 2 to 4, right? Oops. Yeah, from 2 to 4, right? It's on the right subtree. Okay. So yeah, that's pretty much it. And we can keep going, right? So we can go down because okay, and we know that the root, right, will always be the first element in the preorder array, and we need to go in the correct order here. So as we traverse, we need to look at the root, right? We need to traverse to the left side first before we traverse to the right, right? Because the preorder, we use the preorder to build the root, right? So we need to go to the left first before rushing the right here, right? So we need to go to the left. So now we are in the left here. So we build another root, right, for the subtree, which is 9 here, right? Because we are looking at index 1, right? Index 1 with the value of 9, right? Okay. So after we build the root, of course, we need to update our pointer, right, in the preorder to 20. Okay. And we need to keep going down, right? So if we go to the left, the lower bound stay the same, but the upper bound become the index at the root, which is 9, right, minus 1. So 9 is here, right? Whatever on the left side of 9 is in the left subtree, which is nothing. So 0 minus 1 is negative 1, right? 9 is here, so whatever on the right side of 9 will be in the right subtree, right? But we have to, we are capped at 0, right? So if we go right here, and it become 1 and 0, right? So whenever we find that the left is greater than the right, right? Which means we are out of bound. The left and the right pointer overlap, right? So we just return no. Okay. And remember that I go to the right here because I already finished the root, right, first, and then the left side, and then I process the right side, right? Which is in the correct order here. Okay. So now we finished the left side of 3. Now we can move to the right side. Okay. We can build out the root. It's 20. And then we update um our index, right, pointer to the next one, which is 3 here. And we can either go left or go right, right? We have to go left first. If we go left, the lower bound stay the same. So where's 20? 20 is here, right? So we are looking at the right subtree now, right? So only this part. Okay. So 3 is here. Whatever on the left side of 3 is on the left subtree, and whatever on the right side of 20 will be in the right subtree, right? So the upper bound is equal to the index at the root minus 1, so 2 and 2. And if we go right, upper bound is the same, right? Lower bound become mid in the root index plus 1, so 4 and 4, right? Okay. And we need to keep going. So now we need to traverse to the left first before the right. So we will left, we need to build the root, right? 15 here. right? And we increase the index. Okay. So I'm just gonna speed up here. If we go to the left, lower bounds are the same. This become 1. If we go right, upper bounds are the same. Lower bound become 3, right? So because this is our bound, we can just return no. Then for this part, right, I finish the root, right? I finish the left, so I process the right here. Okay. So now I finish the left, right? I finish the root, I finish the left. Now I process the right side. I figure out the root, 7, right? Update the index. That's our bound. So I go left and right, right, left. Be 4 and 5, 4 and 3, and then 5 and 4, right? Our bound, so we just return no. And now we have finished building our tree from the Inorder and Preorder array. It will look exactly the same as this, right? So overall, the strategy is that we will use the Preorder to build out our root, because we know that in for the Preorder array, we always process the root first, right? So if the Preorder is stored like this, right? It's they're gonna have the, what is it? 3 9 20, no, no, right, for these two, and then 15 7, right? It would be much easier, but we don't have that, right? They just compress the tree as much as possible. So that's why we need the in-order array here, right? So again, pre-order is for the root, right? And in-order is to, after we know the root, right, we need to use the in-order to see what is the interval for the left and what is the interval for the right, for the valid left and valid right. Because we know whatever on the left side of the root, right, will be on the left subtree, and whatever on the right of the root will be in the right subtree, right? Because if for the in-order array, we process left, root, and right in that exact order, right? The top complexity would be O of n, right? But however, how do we get the index of the root, right? Every time. So every time we fill out the root value, how do we get the index of the root in the in-order array? So that is O of n, right? So is so that would give us to the time complexity of O of n squared. So instead of using a radar index of, we can have a hash map to store the index of the in-order array, right? So value to index. So 9 at index 0 here, right? 3 at index 1, 15 at index 2, 20 at index 3, and then 7 at index 4, right? So we can build out this first, right? We take us out of n. So it would be around 2n, right? We ignore the constant. So it would be of n, right? So we speed up the operation in a chain for some space, right? The trade-off is space, because we need a hash map to store the index, right? So the space complexity will also be of n, right? And of course, we don't need to worry about duplicate values, because here, pre-order and in-order consist of unique values. So there cannot be any duplicates. Okay, so that's it. Let's code this up. So we need to have our pre-order index, right, for the root, remember? And then um, we need to have a function, right, for build, which is build tree, right? We can take in the left and the right. The left is 0, the right is the in-order length minus 1, right? So the index as the two at the two end. And then we need to have a hash map, remember? To store the value to index of the in-order array. So we can call it value index, right? And then we can do in-order dot for each, right? Value. We can set the value to index of value equal to I. And we need to add the I here, index. Okay. Hello. Okay, yeah, so this will be our hash map, right? From the value for the index. So can we look up the index in constant time. So we need to build our helper method here, right? We see the build. So again, if left is greater than right, which means we are out about, right? So there's no valid left, there's no valid left or right, except three left, right? So we're just gonna return now, okay? Otherwise, we're gonna look at the root value, right? The root value will always be the preorder, right? Remember? And we have our preorder index, right? And we need to be out the actual node. It is just the value, right? So the root have to be equal to the new p node of root value, right? And we need to set the root dot left equal to something, right? The root dot right equal to something, which is the recursion call here, view, left and right, view, uh, left and right. We need to return the root at the end. Okay, so if we move to the left, what does it mean? It means that the lower bound stay the same, right? Yeah, but the upper bound, which is the right, become the index of the root minus one, right? So how to we can get the index of the root? We can go value to index, right? Root value minus one. Okay, we can do the opposite for the right. If you go right, the upper bound stay the same, but the lower bound become the index of the root plus one. And remember, it is the index here is in the in order array, right? Because only in the in order we know, we can know that the root is in the middle and the left is on the left, the right is on the right. And yeah, that's pretty much it. Let's give it a try. Okay. Somehow we got into a infinite loop here. Oh, we forgot to increment our preorder index after we read the value, right? So that might be the issues. Let me try it again. Okay, accept it. And it worked. We're doing very well with the runtime here. So thank you for watching.